In this lesson, we're going to talk about what a buffer is and how it works. We have several objectives. First, we're going to introduce buffers and explain why they're important. Then we're going to explain how buffers work. And lastly, we'll learn to identify buffers. So first, why are buffers important? Well, to understand this, it's helpful to look at some common substances and their pH. In the top right here, I have some red blood cells. So here are some red blood cells. Those carry around oxygen in your bloodstream. And in the bottom right, I have some orange juice. Orange juice we commonly drink. And let's think about what's going to happen to that orange juice when we drink it. Well, it's going to go down to our stomach and then into our small intestines. And eventually, the nutrients in that orange juice, including the citric acid, which is a little acidic, as we'll see, is absorbed into the bloodstream. So ultimately, when we drink our orange juice, some of that is going to end up in our bloodstream. This actually poses a problem because when we take a look at the pH of blood, it's just above 7, about 7.4. And that actually is the exact pH our bloodstream has to be at in order for those red blood cells to work. If I lower the pH of these red blood cells, they start to denature. That means fall apart basically and stop working. And then they don't carry oxygen, which by the way, you need to live. And notice when we look at orange juice, it has a pH of just a little greater than 4. And so adding the orange juice to red blood cells is not going to be a good idea if you want to keep breathing. So what is your body going to do? Well, it turns out it uses a buffer. It uses a buffer in your bloodstream, and what that buffer does is it resists changes in pH. And so that means even though I come along and I drink the orange juice and some of the acidic components of that orange juice end up in my bloodstream can handle it because it's buffered. So a buffer resists that change in pH. A buffer stops the pH from changing. So maybe it would have dropped because orange juice is acidic and now it won't. All right, so that's what a buffer does. It resists changes in pH. Really important to get that. It resists changes in pH. How does it do that? Well, let's start by taking a look at the buffer system our body uses. Here you'll notice that there's 2 compounds present, and buffers always have 2 compounds. They always have a weak acid or base and its conjugate. In this case, this is the weak acid. We'll explain why it has to be weak in a second. All right, now, how can we identify that as the weak acid? Well, there's a good rule here that's helpful when we start to look at buffer systems, which is acids always have more H's. Okay? So when I look at these 2 compounds, we'll notice that one of them has 2 hydrogens and one of them just 1. And so the acid has to be the one with more hydrogens, hence the H2CO3 is the acid. What about this other guy? NaHCO3 is really special. It's not just a random compound, it's really closely related to the one above it. The way we can tell is that if I put this in water, it's going to split apart. It's going to split apart into Na+, and the other compound that'll be left behind will be HCO3-. Because it's an ionic compound, it falls apart. Notice, this is actually the conjugate base of this acid. Remember, when we drop a hydrogen from an acid, we make its conjugate base. So right here, we get the conjugate base of our acid. All right, and so that's what's important. The sodium actually doesn't do anything. It just floats around in your bloodstream, and it's kind of irrelevant. It's the HCO3 and the H2CO3 which are so important. And whenever we want to make a buffer, we need both of those. So second really important point to remember. Buffers contain a weak acid or base, so it can be either a weak acid or a weak base, and its conjugate. In this case, we have a weak acid and conjugate base, but you could make a buffer system that was a weak base and its conjugate acid. Both will work. Why do we need the acid to be weak? It's very important. A strong acid doesn't work. It has to be a weak acid. Remember that weak acids only partially dissociate, and that means that their reactions are determined by equilibrium type math, and Le Chatelier's principle, which we learned previously, applies to them. What does that all mean? Well, let's take a look and think about it. Here's the reaction that occurs between the H2CO3 in our blood and water. When I take carbonic acid, which remember is the weak acid in our buffer system, and I react it with water, we get out our conjugate base and H3O+. So remember that H3O+ is what determines pH. So when I take the negative log of that concentration, that determines pH. And now we see, once again, in a reaction, our weak acid and our conjugate base. So we have both of those hanging around, and that's really important. Then, last thing to note here before we think about what's going to happen when we add an acid or a base is they're in equilibrium. Because it's a weak acid, it doesn't completely dissociate, and that means these things are in balance. And so if I perturb one side or the other, then it's going to shift around to reestablish that equilibrium. So let's say, for example, that I take acid in the form of orange juice. So orange juice is acidic, right? And I go ahead and I add it to our bloodstream. Well, if I have this buffer system around, then that acid has something it can react with. What is an acid going to react with? Would it react with the weak acid or the conjugate base? Well, an acid is going to react with base. Remember, they're opposite. So what's going to happen is my orange juice that's acidic is going to come over here and it's going to react with my conjugate base. Now, initially what that does is drops the concentration of my conjugate base. But the equilibrium established by Le Chatelier's principle immediately restores some of the concentration of that base. So I've taken away from the right-hand side, and as we remember from Le Chatelier's principle, that means that our equilibrium will shift to the right, and it will keep the amount of base and the amount of acid relatively constant. So the key thing here is that Le Chatelier's principle keeps the concentration of acid and base about the same, and that's why the pH doesn't change. So weak acids and bases establish an equilibrium, and that's why we need them to be weak. That's why a strong acid wouldn't work. It just completely dissociates, and Le Chatelier's principle doesn't do anything. Okay, so what we've learned so far is that buffers resist pH and that they require a weak acid or base and its conjugate. Now, if you need to have a weak acid, you need to be able to know when you have a weak acid or when you have a strong acid. And so it's helpful to remember this list of strong acids and bases. I will go ahead and take a picture of this. You could write it down. That's the old school way to do it. But go ahead, take a picture. And remember that if something you see is not on this list, then it's probably a weak acid or a base. So if it's not on this list, then assume it's weak. All right. And that's how you're going to be able to identify weak acids and bases. Now, ultimately, if you have to Google something like this, that's fine. Of course, you won't be able to on a test. So for a test, you want to have these strong acids and strong bases in mind. But ultimately, some acids you just have to Google to confirm if they're weak or strong. All right. Now, these are the strong acids or bases. So anything not on this list is weak and might be able to make a buffer. Let's go ahead and practice identifying a buffer. Which of the following pairs are buffers? Well, in our first pair, we have HF and NaF. Let's take a look at our steps to figure out if it's a buffer. Step 1, identify the acid and the base. Okay, so we're going to identify the acid and the base. Well, when I look at HF and NaF, which one has more hydrogens? That's right, HF. So that's going to be the acid. So HF is my acid, and that means NaF is going to act like my base. All right, so we've identified the acid and base. Now we should identify the conjugate by dropping an ion. Here, it's a little tricky to kind of learn this pattern, but when I look here, what ion do I see that's just going to dissociate and fall away? It's not on both of them, it's just on one of them, and it's going to fall off, and it's not going to matter. It's the sodium. And so the sodium is going to go away. It's positively charged, so it's going to leave behind F-. All right, so that's the first two steps. We've identified the acid and base, and we've identified the conjugate salt by dropping the ion. Now we want to double check that we have a weak acid or a weak base. All right, so if I look at HF, right, that's the acid, and is it on my strong acids list? No, it's not. HF is a weak acid, and in fact, it's one of the most common weak acids. So this is a weak acid, that's good. And then last step, if I have a weak acid and its conjugate base, then I have a buffer. Okay, so I have a weak acid, check. And this is its conjugate base because notice if I just drop off the hydrogen, I get a match between those two. They're both just Fs. So I have there a common ion. They both have F-. They have a weak acid and its conjugate base. So this actually is a buffer. So this top one is a buffer. Hooray, a buffer. And it could resist changes in pH. It would have an equilibrium. If I add an acid, it'll react with the base and then rejigger around to keep the pH constant. Let's do the same thing with our bottom one here. Now, first, let's identify the acid. This one has an H. This one has no H's, so we know HNO2 is our acid. We'll decide later if it's weak or strong. We'll generate the conjugate by dropping off the ion. So here, sodium is our ion, and we'll be left with NO3. It will be negatively charged because our sodium is positive. So that's going to be our base. Okay, then let's go ahead and see if we have a weak acid. Is HNO2 on our strong acids list? One really close to it is HNO3, but that's a different acid. It has an extra oxygen. So no, it's not on our list, and therefore it's a weak acid. So this is a weak acid. Okay, last step, we need to double check that we have both a weak acid, check, and its conjugate. Well, here actually we don't have its conjugate. Notice if I box the ion here, do they match? No, one has 3 oxygen and one has 2 oxygens. So this is actually not a buffer. It wouldn't have an equilibrium. It wouldn't keep the pH from changing. You need a weak acid or base and its conjugate. All right, let's practice identifying buffers with some basic compounds. Now let's take a look at these two pairs of compounds. First up, we have NH3 and NH4Cl. Again, we'll apply the same rules to identify the acids and bases. We'll look for the one with more hydrogens. This has 3 hydrogens and that has 4. So that tells me that NH4Cl is my acid. And it tells me that NH3 is my base. Okay, so we have a base and an acid. Now we're going to generate the conjugate by dropping off an ion. All right, which ion's just going to fall apart? Which ion's just going to fall off? It might be a little hard to spot here, but it's the chlorine. The chlorine is going to have a -1 charge in solution and just fall away, so that chlorine just goes away. And when that chlorine goes away, it leaves behind the NH4 charged. Okay? Now we're going to want to go ahead and look and see if it's a weak base or a strong base. Notice because this guy is a conjugate, we don't actually worry about it. We know that's going to be a conjugate because we dropped an ion to get there. So we don't want to check for that one. We want to check for the base. And when we check for the base, we don't see NH3 anywhere. And so what that means is NH3 is in fact a weak base. And that's actually a very common weak base that you'll see over and over again. So it's a good one just to commit to memory as a weak base. All right, then we want to ask if we have the conjugate. So we do have the weak base. Do we have a conjugate? Well, notice these two are related just by the gaining and losing of a hydrogen. They're exactly the same, except for one of them has an extra hydrogen. So that means we do, in fact, have a conjugate acid. So there's our conjugate acid, and we have a weak base. So yes, that's a buffer. All right, let's look at the next one. NH3 and NH4Br. You'll see this one looks pretty similar, and you'll see lots of small variations on this same problem where NH3 is the weak base because, like I said, it's just a very common base to see. So we know NH3 is already the weak base. We've talked about that. And then we'll generate the conjugate. Well, here what falls off? Well, just like the chlorine fell off before, now the bromine falls off, and we're left with NH4 plus, which is going to be our conjugate base. Notice it's actually the exact same buffer system as the one above. So it turns out this little ion that you add on to the end of your conjugate doesn't really do anything. It just falls off. And this system is identical. So both of these are a buffer. So yes, this bottom one is also a buffer.